In this video, we are going to be looking at vectors, forces, moments, Hooke's law, and more stuff about forces, okay? So a very easy one to start with, the difference between a vector and a scalar. So essentially, a vector has both magnitude and direction, while a scalar has magnitude only. That is the difference between a vector and a scalar. So in this table, we have some quantities given to us, and we have to classify them as a vector or a scalar. And the first one was done for us, which was mass. So momentum is a vector, okay? Displacement is a vector. Heat capacity is a scalar. Temperature is a scalar. Half-life is also scalar. And upthrust is a vector. Alright, an easy 6 marks there. A taxi reaches a traffic police officer while traveling at 30 meters per second on the highway. The officer immediately signals the taxi, which decelerates uniformly and comes to a complete stop in 5 seconds. In the space below, draw a velocity time graph to represent the motion of the taxi from the moment the officer signals to when the taxi comes to a stop. So this is just a scrappy graph here. So over here is velocity. And over here is time. It's a very easy graph actually. So he is at 30 meters per second over here. So he's traveling. And then he comes to a complete stop in 5 seconds. Sorry, oops. That was not meant to happen. Okay, so in 5 seconds, he comes to a stop. So he decelerates uniformly. Determine the distance traveled by the taxi from the time the police signals until the taxi stops. So to calculate the distance, you need to find the area under the graph. And it so happens that this area is a triangle. So the area will be base by height over 2. So my base is 5, my height is 30, and over 2. So this will simply be, well, the 2 could cancel into the 30, you get 15, and 15 by 5 is 75. So 75 meters will be my answer here. If the speed limit is 80 kilometers an hour, determine whether or not the driver should receive a speeding ticket. So what they're asking us here is to convert the 30 meters per second into 80 kilometers an hour. So that's kilometers an hour. Okay, so we have 30 meters per second, right? So we have 2 things to convert here. We have the meters to kilometers and the seconds to hours, okay? So 1 kilometer is 1,000 meters, and 1 hour is 3,600 seconds, right? So we have to do them separately. Okay, so if we have 1 km to 1,000 meters, then 1 meter would be 1 over 1,000 kilometers, and 30 meters would be 30 over 1,000 km. We could agree on that, right? The next thing now is to convert the seconds to hours, right? So 3,600 seconds makes up 1 hour. So 1 second would be 1 over 3,600 hours. Alright, so what we have to do is take the distance, the kilometers, and divide it by the hour. Because that's what this means, you know. The -1 here means that we are dividing by the hour. So 30 over 1,000 divided by 1 over 3600, and when we are dividing fractions, we simply flip it and multiply. So it's going to be 3600 like this, and these zeros could all cancel off. So we end up at 36 multiplied by 3. Let's see what that would be. Let's whip out my calculator here. That is 108 kilometers an hour. So yes, he should get a speeding ticket. Okay. The container shown below is completely filled with cement. Okay, and we have the dimensions of the container here. If the mass of the cement is 15,000 kilograms, calculate the density of the sample. Very easy. So density is your mass per unit volume, which means mass over volume. So what we need, we get the mass here, but we need to calculate the volume. So the volume is simple, length by breadth by height. It's a cuboid, right? So you have 1.1 by 2 by 2.5. All we need to do there is punch that in our calculators, and we will be able to get the result. 1.1 by 2 by 2.5, 5.5 meters cubed. So now I can take my 15,000 divided by 5.5, and I will get 2,727.27 kilograms per meters cubed. What pressure in newtons would the cement exert on the base of the container? So there's another new formula. So pressure is force over area. Right? So we have the mass of the cement, but we need to find the weight of the cement. That will give us the force, right? So the weight is simply the mass, which is 15,000 multiplied by gravity, and they told us what gravity is, 10. So essentially we have 150,000 newtons is our force, and the area is the base of the container, right? So we have a new something to calculate there, right? We need to get the area of the base. The area of the base is very easy. You take this one and you multiply by this one. The height does not play a part in the base, right? So we get 1.1 by 2. 1.1 by 2 is simply 2.2 meters squared. Okay, so I have my force, which is 150,000 over 2.2, and my answer is 68,181.81. Okay, and this is Newton per meters squared. Alright, so very simple formula here that we need to remember, right? Density is mass over volume, pressure is force over area. Okay, so this is a new topic now, which is Hooke's law and elasticity, right? So again, with definitions, I like you to use your own definitions, right? But generally, Hooke's law states that the displacement or the size of a deformation of a spring is proportional to the force or the load that is causing it to be deformed, right? So essentially, if you have a spring here, right, and you put a weight on it, the weight is going to stretch out the spring, and that amount of stretch is proportional to the weight of the load that you put on it. Okay, so you could come up with your own definition there from your favorite note or textbook, right? So with Hooke's law, we have graphs that depict Hooke's law. Okay, so I'll draw the graph here. Alright, so the Hooke's law graph, you have your force, which is the force of the object that is pulling down on the spring. And we have extension, which is the amount that the spring, sorry, I keep saying string, is going to extend, right? So every spring has a limit to which Hooke's law could apply. Obviously, just think about like a rubber band or something. You could stretch the rubber band a lot until it bursts. After that, it's not going to go back to its original shape, right? So for a certain portion of the graph, it's going to be directly proportional to the force, right? The extension and the force are going to be proportional. So anywhere along this line, if you were to remove the weight, the spring would go back to the way it was, right? And there's in every spring, there's some kind of limit, right? The limit of proportionality or the elastic limit. So after this elastic limit, any more force will cause the graph to look like this. Right? So as you can see, it's more like a curve there instead of the straight line. So at this point, the spring cannot take any more. The spring will break. At this point is the elastic limit. Okay? So we have drawn the graph, but now we need to explain what the elastic limit is. So the elastic limit is the greatest amount of weight or force that can be applied without causing permanent deformation. Okay, so as long as you remove the weight before the elastic limit has been surpassed, the spring will go back to its original shape. Okay. Okay, so here are some questions based upon Hooke's law. A steel spring has a spring constant of 2 by 10 to the power of 2 Newton per meter. Calculate the weight of an object which, when attached to the unloaded spring, produces an extension of 50 millimeters. So notice already we have meters here and then we have millimeters, so they're trying to trick us already. Okay, so now it's important to say that the elastic limit is not exceeded because our formula would not work, and they have so nicely given us the formula here. So every spring has a spring constant. That will determine how much it extends and stuff like that. They will actually give us that, right? So we could call the spring constant Q is equal to force over E for extension, right? Now they want us to find the weight or the force. So therefore we need to make F the subject of the formula, and this is very easy. E is being divided here, so we just need to multiply by E, right? So we have Ke will be equal to F. Right, so now you have to change the 50 millimeters to meters. Okay, now a millimeter is 1,000. Sorry, a meter is 1,000 millimeters, right? So in order to change that, we need to divide by 1,000. So 1, 2, 3, we will get here. So we add 0.05 meters is 50 millimeters, right? So the K is 2 by 10 to the 2, which is essentially 200, multiplied by 0.05 will give us the force. Let's see what that would be. 200 by 0.05, and our force is 10 newtons. Right, very simple calculation. The next part, the object attached to the spring in B fell from rest and hit the ground after 2 seconds. Calculate the velocity of the object on hitting the ground. Okay, so this let us try to throw in some kinematics there for us in the formula, right? So we have four kinematics formulae. If you watch the previous video, you would have seen that, right? So let's see which one we could use. Now they already give us acceleration here, which is g. All right, we'll call that a. Now we have the initial velocity, u. We have the final velocity. It hit the ground, so it's already again 0. And then sorry, on hitting the ground, my apologies. So they want us just before it hits the ground is going to be v. And then we have the t, 2 seconds. Okay, so we have a number of different formulae that we could use there, right? We want to find v. So we have v is equal to u plus at. I think that one is going to be the easiest one. 0. Okay, so you get 20 meters per second. Okay, in this last section, we'll be defining moments. So the moment of a force is the product of the force by the perpendicular direction to the pivot, right? You could find this definition anywhere. And the second part is to draw a diagram to illustrate the action of a force multiplier lever. So levers could be either force multipliers or distance multipliers. Force multipliers being something like a crowbar. So for example, if you had a load here and you wanted to lift this heavy load, you could put a fulcrum, put a crowbar here, right? And you will be pushing down on the crowbar in order to lift the load up. Right, and what you need to pay attention to is the distance from the load to the fulcrum and the distance from the effort, which is the force that you are putting to the fulcrum. You could see that the distance from the effort to the fulcrum is longer than the load to the fulcrum, and that is the operation of a force multiplier lever. Okay, so here we have a wheelbarrow. Okay, and we have to do some calculations on this wheelbarrow. So we could see that we have the handles there that somebody would be lifting the wheelbarrow. Then we have the weight of the wheelbarrow here, that's the center of gravity. That's another force going there. And then we have the wheels, which would act as the fulcrum, right? So we need to identify the nature and point of action of the third force on the wheelbarrow. So there are 3 forces acting here and they give us 2. The 2 being the applied force and the weight. Well, the third force is going to be at the wheel, right? Because from Newton's third law, right, the wheel is obviously exerting a force down on the ground, and the ground will be exerting an equal and opposite force on the wheel. So there's a force going up here, right? And we'll call this R, the resultant force. Right, so this is the nature of the force, right? And we need to write down an equation showing the relationship between the 3 forces. So they said that this is an equilibrium, which means that at this fulcrum here, so the wheel is the fulcrum, so R will be equal to any of the other forces on the opposite side of it, right? So R is an upward force, so that means the applied force will be a positive force, right? So we'll have to say that the applied force F, and it's 1.5 meters away from the fulcrum. So 1.5 F, that's the formula for moment, the product of the perpendicular distance and the force, minus the weight, because as you can see, the weight is in an opposite direction than R. So we have to assign it a negative value, minus 0.6 by the weight, right? So the weight is actually 0.6 meters from the fulcrum. And this is the equation that relates the 3 forces. The next part of the question asks us to calculate the weight first of all, which is very simple. It's 43 by 10, which is 430 Newton. And then they want us to calculate the value of the applied force. And this is actually quite simple, right? So the applied force, we'll have to use moments for all of them. So the moment about R, we don't need to find what R is, because R is 0 meters away from the fulcrum. R is on the fulcrum. So the moment of R is actually 0, right? So 0, we're using the same equation here, is equal to 1.5 F, that's what we're trying to find, the applied force, minus, and we have the weight now, right? So 0.6 multiplied by the weight, which is 430. And why we are doing it minus is because the weight is in the opposite direction from the thing that we are trying to find, F, right? So now we have 1.5 F minus, and we can put this in our calculator, 0.6 multiplied by 430 minus 258, and we can move the 258 to the other side. So the minus 258 will become positive 258 is equal to 1.5 F, and to find F we simply move the 1.5 to the other side. So we get 258 divided by 1.5 is equal to F, and that would give us 172 newtons is F. Alright, very simple there, moments calculation. And that brings us to the end of this video.